So we have a cell.
Which for neurons is -70, right?
Mm-hmm.
-70 millivolts or whatever. Okay.
Exactly. So it's more negative on the inside than it is on the outside of the cell,
Yeah,
resting.
because of the proteins.
Because of proteins. Yeah, the proteins are negative.
Slightly negative charge.
Also, the sodium-potassium pump contributes to where the membrane potential rests at.
Okay.
So how many sodium are being pumped out? And how many potassium in?
2 or 3 out, 2 in.
Okay. Exactly. Now, potassium, it's kind of the main ion that contributes to the resting membrane potential. He's kind of the ultimate, I guess, factor in deciding where that resting membrane potential stays. And that's because there's leak channels for potassium.
And there are more than there are for sodium, or there just aren't any for sodium?
There isn't any for sodium. So sodium's being pumped out, but there isn't any for sodium. So there's
sodium potassium pumps are always active transport then, is that right?
Yes. Yep. Going against their gradients.
Okay.
So potassium will build up in here, right? Say if these gates were closed, potassium would build up, right?
Uh-huh.
So the membrane potential would continuously get more and more positive.
Okay.
But since there's leak channels, it eventually kind of reaches an equilibrium where some's coming in, some's coming out, and it stays around
Just
70.
stays in a normal range.
So what do you think? What would happen if I just made another leak channel? What would happen to the charge of the inside of the cell?
Well, would it just take longer to get to equilibrium? I mean, eventually wouldn't it get there anyways? Regardless of how many there are?
Well, but the equilibrium could change where equilibrium's at. So what if I made another, right here, let's say it's at -70. What if I added another one? Now more potassium can leave.
Then it's going to go further negative because
Yeah.
there's less positive charge in the cell.
Exactly. So that's kind of the whole, one of the main principles, like the electrochemical gradient,
Okay.
is positive ions leaving, leaves it more negative on this side. But there also is a desire for potassium to come back in because it's negative in here, right? So its concentration gradient is pulling it out, but then it wants to come back in.
Just because of the attractive.
There's an yeah, so that's what electrical chemical gradient is.
Now, with all the ions that we usually talk about, potassium is the only one that is more concentrated inside than outside. Is that correct? Or is it the other way around?
Yeah, potassium is more concentrated inside than outside.
Inside, and the other 3 are more concentrated out for the most part. Like
Sodium, calcium, chlorine,
Yeah.
all want to come in.
All wants to come in. Potassium wants to go out.
Yes.
Okay.
So say you have a beaker right here. This is just trying to help understand the concept of the electrochemical gradient. You have a beaker right here. The membrane is only permeable to potassium ions. Okay. And there's water. If I put a bunch of potassium chloride in here, what happens to the ions when they get in water?
I don't know if potassium chloride dissociates or not.
It does.
Okay.
Any ionic compound dissociates.
Okay.
Because this is a positive and negative.
Positive, got it.
So you got a positive and you got negatives. Say I put a bunch in here, right? So there. Well, what's going to happen to these potassiums? Are they going to stay here, all of them, on this side?
If it's permeable to potassium, then no. They'll have to move somewhere.
Exactly. Permeable potassium, so some of them are going to leave this side, just because the concentration gradient is going to pull them this way.
Okay.
Now, what would make them want to go back?
The negative charge.
Yep. The electrical gradient is pulling them that way.
Okay.
So chemical is the same thing as basically a concentration gradient.
Okay.
So chemical gradient's pulling it this way, electrical gradient's pulling it back.
Okay.
So they're kind of good. They're going to come out, but they're going to come back in. It's kind of like this cycle, right?
And
Until
it keeps going until it hits the resting membrane potential or an equilibrium?
In equilibrium,
Yes. Okay.
exactly, resting membrane potential. Because it'll eventually get to a point where the rate at which potassium flows this way is equal to the rate at which it flows this way.
Okay.
Doesn't mean they're necessarily going to be equal, because which side do you think would probably, well, I don't know if we can determine that, but it's not going to be equal, right? Because there's different forces pulling on it.
Okay.
But the rate at which they flow.
Okay, so the natural current is pulling it that way, but the attraction to the electric chemical is pulling it
That
back.
way. Exactly.